Okay, this is Accel Algebra 2, lesson 2.7, and the concept is inverse functions, and there are 7 boxes I'd like to talk to you about. So let's get right into box number 1. Let's talk about inverse functions and the basic idea of what an inverse function is. So on the left-hand side here, I have a function f of x is equal to 3x plus 2, and on the right, I have a function that says g of x, which is equal to x minus 2 divided by 3. So what I want to do is just some basic ideas. So if I evaluate f of 1, for example, then f of 1 would be 3 times the number 1, and then plus 2. That would give me 3 plus 2. That would give me a value of 5. That's not really a big deal. So f of 1 gives me 5. Means I put in a 1 for the f function and out pops a 5. Now, check this out. If I go over to the g of x function and I evaluate g of 5, for example, look what I would get. I would get 5 minus 2, all divided by 3, which of course is 3 over 3, which of course is 1. So I'm not sure if you caught what happened there. I took the number 1, okay, I evaluated f of 1, and I got the number 5. Then I took the number 5, and I evaluated g of 5, and I got the number 1 back. So notice that 1 became a 1 again when I ran it through f and then g. This is what's known as an inverse function. G is an inverse function of f. So what that means is it undoes everything that f did. So the domain of my f function, which was 1, became the range of my g function, and the range of my f function became the domain of my g function. So these functions are inverses of each other. So what we wouldn't call g of x just by itself. What we would do is we would call this f inverse of x. So that's how we say this. This is f inverse of x. So that doesn't mean 1 over f of x. It means f inverse. So what that means is it undoes the function f of x. And this is the basic idea of what functions and inverse functions and how they behave. Basically, their domains and their ranges switch, and they undo each other. So this is where we're going to start, and this is what we're going to explore today in this lesson. Okay, here's box number 2. Let's explore for just a moment how you could find the inverse function algebraically to a given function, okay? So let's say I have f of x is equal to x plus 4 divided by 7. The first thing I would do is I would interchange f of x for y, so that we're working with coordinate points x and y. So y is equal to x plus 4 all divided by 7. Then, if you recall from box number 1, all that happens is the domains and the ranges switch places. So all domains are x values and all ranges are y values. So I'm going to go ahead and switch those. So x is now equal to y plus 4 all divided by 7. And then I'm going to go ahead and resolve this for y. So multiply both sides by 7. So 7x is equal to y plus 4. So therefore, y is now equal to 7x minus 4. So now, I now recall y f inverse of x is equal to 7x minus 4. So what can we do to check to make sure that this is correct? So watch this. If I take f of 1, for example, okay, it would be 1 plus the number 4 all divided by 7. That would give me 5 divided by 7. Now, if I take f inverse of 5 over 7, notice I would get 7 times 5 over 7, and then minus 4. Well, that would just give me 5 minus 4, which would give me back the number 1. So exactly what I started with. Once over, the way that you could check to verify that a function is indeed an inverse of itself is you can use function composition. So what we want to show is that f of f inverse of x is equal to itself x. So what that means is when I compose one function with another function, all I get back is the x value. And I'm going to show you how to do that in the next box. Okay, here's box number 3. It says find f inverse of x and verify that it is indeed the inverse. Okay, so let's follow the same exact steps that we did before. So I'm going to say y is equal to the square root of 2x minus 3. Then I interchange x and y, so x is now equal to the square root of 2y minus 3. And again, we do that because our domains and our range values are going to switch. Then I am going to square both sides because I want to resolve for y. So I get x squared is equal to 2y minus 3. And now solving for y, I get x squared plus the number 3, all divided by 2 is equal to y. So the inverse function of x is now equal to x squared plus 3 all divided by 2. Okay, now that's the easy part. Let's go ahead and verify. And notice I'm going to draw two columns for you because in order to verify, you have to do two things. You must show that f of f inverse of x is equal to x, and you also must show that f inverse of f of x is equal to x. So you must do function composition twice. So I'll call this number 1 and I'll call this number 2. You have to do both of them. Okay, so let's do f of f inverse. That's f of x squared plus 3 divided by 2. So again, I take all this information and I plug it into the f function. So I'm going to have the square root of 2 times x squared plus 3 over 2, and then minus 3. Okay, so 2 times all the stuff divided by 2, that cancels out. That leaves me with a big square root of x squared plus 3 minus 3. That leaves me with a big square root of x squared, and that leaves me with a value of x on its domain. So that's good because we want to show that's equal to x. Likewise over here, we must do the opposite, f inverse of f of x. So I want f inverse of f of x, which is the square root of 2x minus 3. So therefore, I'm going to take all this information and run it into my inverse function. So I'm going to take the square root of 2x minus 3. I'm going to square that. I'm going to add 3, and then I'm going to divide by 2, because that's what it says right here. That's my inverse function. So the square root of 2x minus 3 squared, of course, is just 2x minus 3, then a plus 3, and then divided by 2. So this leaves me with 2x divided by 2, which leaves me with a value of x. So now I have completely verified that it is indeed the inverse by showing f of f inverse is equal to x, and f inverse of f of x is equal to x. Okay, here's a challenge problem. Here's f of x equals 3 minus x over 5x plus 4. Just find the inverse. Try it on your own and then hit play and I'll show you the solution. Okay, the answer is 3 minus 4x over 5x plus 1. So how did I do that? The first thing I did over here was I interchanged my f of x for y. Then I switched all my x's and y's together. Then I multiplied both sides by a 5y plus 4. Then I distributed in this step here that I'm highlighting. Then I gathered my y terms together. I factored out a y, and then finally divided by a 5x plus 1. So a lot of algebra in that one, but hopefully that makes sense to you. Okay, in box number 5, I want to talk to you about the specific graphs of inverse functions. So the blue graph here is the linear function 3x minus 4. The green graph is the inverse to that function, which is x minus 4 over 3. And then the line down the main diagonal, is the line y equals x. So I want you to take a look at these individual points, okay? This point right here, negative 1.33 comma 0, and this point right here, 0 comma negative 1.33. Hopefully you notice something. This point over here, 0 comma 4 on the regular function, and then 4 comma 0 on its inverse. And then this one, of course, stays the same. So hopefully you're noticing that all you have to do to graph the inverse of a function is basically switch the x and the y values, right? If the point 0, 4 is on the function, then the point 4, 0 has to be on the inverse. And this makes sense to us because, remember, all we do is we switch every domain for every range. So we get this nice, beautiful, symmetric graph about the line y equals x. So this is an important role in looking at the graphs of inverse functions. So all I wanted you to do in box number 5 was get a sense of, okay, if a point is on my function itself, then if I switch the x and y coordinates, then that point has to be on the inverse function. Okay, here's box number 6. Let's sketch the inverse function, okay? I have the point negative 8, 0. I have the point 0, 4, I have the point 3, 3, and then I have 7, 0, and I'm calling this thing f of x, okay? So if I wanted to take a look at the inverse function of this, instead of negative 8, 0, I would have 0, negative 8. I would switch the x, y coordinates. Instead of 0, 4, I would have 4, 0. 3, 3, you can see, is right on the point, right on the line y equals x, so that's going to stay there. And then instead of 7, 0, I'd have 0, comma 7. So if I connected all of these, I would have this graph right here, and this would be f inverse of x. I didn't do a very good job of keeping my line straight, but hopefully you get the idea of that one. The last idea I want to talk to you about in box number 7 is what's known as a one-to-one function. A one-to-one function simply means that the function itself is a function to begin with, and its inverse is also a function. So one thing that I want to introduce to you right now is called the horizontal line test. The horizontal line test is defined as a function, f of x, has an inverse if and only if it passes the horizontal line test. Okay, so let's explore this. I've given you two functions. The one on the left is x squared. The one on the right is x cubed. Both of these are functions, okay? Why? Because they pass the vertical line test, right? You can clearly see that both of these functions pass the vertical line test. So both x squared and x cubed are functions. However, only one of them is a one-to-one function. If I take the horizontal line test, you can clearly see that it does not pass x squared because I have two different x values for one y value, okay? Even though it's a function, it's not a one-to-one function. Now, if I look at the x cubed function, no matter what horizontal line I draw, it never crosses more than once. So because x cubed passes both the vertical and the horizontal, then that tells me that x cubed is what's known as a one-to-one function. That's sort of the quickest way of understanding what a one-to-one function is. So you're responsible for being able to look at a graph and determine whether or not a function is one-to-one.